Okay, the recording has officially started. Cool. Well, thank you so much for joining. My name is Mohit. I run this user group. The user group name is Cybersecurity Practitioners. I try to attract people to talk about cybersecurity. I talk about cybersecurity here and various things that impact cybersecurity. A couple of days ago, I came across an article and that intrigued my interest in this a little bit more. I love containers, and the security around containers sort of is evolving. But supply chain is also becoming a sort of thing that actually makes it a little bit difficult to share code with everybody else. Yeah. Okay, I hope you could still see it. Before we begin, I'm going to share the information about the user group so that you can find the resources and everything there, whatever we're going to talk about here. So all the sessions are recorded, and whatever I talk about here is available at the GitHub repo also. There's a LinkedIn and there is a meetup page for you to be interested in joining. If in case you want to talk about something, hit me up and we can arrange that perfectly. Cool. Coming back to the topic. Building trust in container supply chain. With this time, we found a sponsor also. We're sponsored by Stack IT. It's a new company that started in 2025. It's completely dedicated to infrastructure. So in case you have infrastructure needs of resource management or cost optimization or backup or customer support or something like that, you can reach out to them. They're available at Stack IT. Stack means strong, IT means IT, and .no. Cool. First things first, because we're talking about containers, we're talking about supply chain, we're talking about pipelines, what's very important and very relevant here is DevSecOps. Because DevSecOps is a practice that I've been practicing a lot with my customers also, in which you break down the whole process of delivery and make sure you attend to individual processes with one aspect at a time. For example, developers do code reviews, static analysis, and penetration testing, and all of those have to be identified as a separate task, because all of those separate tasks, they have their own separate processes and tools to work with. For example, threat modeling is basically an activity in which you hypothetically make the architectural diagram, you try to test what scenarios work and what scenarios don't. There are threat modeling tools that you could use, and this is not part of the coding. This is very specifically architectural design. If it's done good, then the software comes out good, and you do not find vulnerabilities that are just too obvious and that were just out there in the wild to be exploited. Same thing is about threat intelligence and monitoring. There are tools, there are techniques around these that could be used to go ahead and do this, and very specific processes around that too. Same is for testing and code reviews. There are standard tools that give standard outputs that are used to create automations and pipelines for these to have approvals and such. Yeah. And this is exactly what I was talking about. Now, eventually over time, this has evolved into a cycle, a never-ending process that needs to be iterated, needs to be perfected in order to achieve a good software delivery. Now, infrastructure, for example, infrastructure, for example, can be done with the help of AWS and cloud, Terraform, and everything else. Automation has Puppet and Chef around with it. There's a lot of other tools for different stages. And right now, in today's presentation, I'm going to discuss a tool or two that could be used to go ahead to check these things in its entirety so that you do not inherit bugs in your containers from a repo that's not even verified. And the reason why I'm talking supply chain here is because eventually, even in Gartner's list and every other security evaluation over the years, supply chain has evolved as a major threat, because supply chain has a very good possibility of hiding vulnerabilities into credible sources and softwares, which are then used and reused again and again to make bigger and better softwares, which ultimately inherit that one small software that might just possibly open a backdoor. This has happened in Node.js. It has happened in Log4j, a couple of other examples. And these are very fundamental small software that are just used everywhere. And the same thing comes to containers. In case you are new to containers, containers are usually built in layers, which I'll talk about briefly in a bit. But the point is, if even one of those layers is compromised by any software that's installed there, then the whole container is compromised. This is not an exhaustive list of tool sets. You could use many other tools. There are tools that combine a lot of these aspects, but this is just a description from one of the blogs, I think from OWASP, in which they discuss DevSecOps and how security is all over. And the security has to be taken up with the help of these tools, because these tools undergo specific processes that take care of these very specific vulnerabilities of that stage. Now, moving forward, let's take a step back, right? We're talking about containers, but what is containers? A container is basically, in a very, very crude sense, for the unannounced, container is basically a very light virtual machine. It's a Linux construct, but whereas virtual machine has the whole operating system and everything around it, so a large attack surface. What Docker essentially has is a very restrictive executable environment in which the bare minimum of that operating procedure is there. In fact, virtual machine can survive as itself, but containers cannot, because containers eventually use a lot of host machines capabilities, because they do not want that responsibility. So they ship that out to host machine and only keep the relevant infrastructure, code, runtime, system tools, and libraries that are needed to run your code. Not a very good description, but what I'm trying to say is that it's very good at running software in isolation. They usually have only one endpoint, and a web services hosted there can actually benefit from just its environment. So it's possible to run two different versions of the same software on the same machines with the help of containers. Two different containers in the same machine could run two different softwares without interfering with each other. Very lightweight, very extensible, and easy to define with the help of a Docker file. What I'm trying to say here is that they might be comparable to virtual machines, but they're a little bit more than virtual machines. For example, in left and right, you would see two diagrams. One is for virtual machine, the other one is for containers. Both are running on some sort of hypervisor or virtualized system. But the virtual machine doesn't just use everything from hypervisor. It creates its own situation. It gets its own guest operating system, gets its own libraries, gets its own applications. Because of that, it's very heavy, not very flexible, and very honestly, not a great choice to migrate softwares into the modern environment to create software for that, because they're very expensive and very bloated. Hence, a lot of attack surface that can be exploited by the people who want to exploit the application. On the other hand, container takes away the guest operating system, uses the host operating system capabilities most of the time to make sure certain things are functioning, and it just needs those certain things to be functioning. Each virtual machine, each Docker is like a process, and it resides in its own entirety. Doesn't talk to anything else unless and until you establish certain networking things, which is advanced Docker. But it only works with its own executable, its own environment. That's all it does. It doesn't expand the attack service so much so that the random softwares could interfere with your execution. Yeah. Very nice piece of software, but the process of creating Docker is the problem here. Docker itself is amazing. Linux has been using this process isolation for a very long time. The problem arises when this Docker file or the Docker container, the kind of binaries it uses, because it's not like creating a virtual machine, it's a specific piece of software in itself. The image is created specifically for running on Docker. There are a number of images for Ubuntu and a number of Linux that are very lightweight. There are Windows Docker's container too. But all of these containers are mostly done by vendors and the open source community. The problem here is that in the open source community, it's a little bit difficult to verify who is doing or working with what. That creates a problem of untrusted source, because the modern problems have impacted the supply chain a little bit with hacktivism, in which people just want to say something and they take it out on the software that might be having a long-term impact to create a buzz around it. Or you might just pick up an image that was just described very nicely because it fits your specific purpose. And now you're stuck with an image which was inherently created for the sole purpose of penetrating somebody's security defenses. It's not possible to identify who the user on the other side is, what their intent is. So it's very important to verify your base image. Operating system images are mostly by vendors, and you can hold them accountable if something happens. You can companies have licenses with them. Windows, Red Hat, Ubuntu, they all have enterprises licenses, and their virtual machine images are created by them. If you go for another flavor of Linux, which is not supported, that could be attributed to a problem. But containers don't really have that vendor thing. There are vendors who make their own containers, but there are several of open source containers that are just out there, which are more convenient than the vendor containers because they solve that one very specific problem that you had. And that's why it's very difficult to sometimes find a source that's reliable. That's one of the problems. The registries are most often compromised. If a registry becomes famous, they're mostly taken away by people. They're often sold also. So there might be people who've sold their registries after they became a lot more famous. Then there are dependencies and environments. It might be possible that the environment that you've created or the environment that you're executing in your Docker, that might be compromised too. The whole pipeline could be unverified and undeployed. Plus, because the more isolated this thing becomes, the less visibility it has. There's a huge problem about the visibility of what's exactly being executed in your pipeline in Docker. Because if something happens, or even if nothing happens, you do not have an indicator of how good this is. This is where I introduced Microsoft Container Secure Supply Chain Framework. Quite a mouthful, but an important concept. This framework basically breaks down this process of getting through the Docker deployment into such digestible portions that you can address small things. And you could go ahead and work on one specific aspect. And for each of those aspects, it defines a couple of tools, not just Microsoft tools, there are other tools too. And it defines a couple of processes and defined outputs that basically gives you that feeling of control there. Builds is used for the following steps. So first, we identify what supply chain stages are there for containerized apps. Then we outline the risks and the required security controls for each stage. Then we describe the security objectives of what do we want from that. We describe tools, processes, and then eventually we go ahead and maintain that thing. That's DevSecOps for you. This is the official Microsoft diagram. So you acquire the image, catalog whatever is in the image, you build the image, and you keep it in your trusted repository, and that's where you refer it from, deploy, and run it from. So we acquire the container image from an external third party. We catalog whatever is there in the image. If one of those things is verified or tagged or flagged somewhere, Microsoft Tools or any other tool that you use for it, which we'll see, which we'll do that right now. It's possible to go ahead and see if particular software or binary is compromised. So you could identify that during the catalog stage. After you've identified, after you do the baselining, after you do the hardening, you can build a hard image that the organization is comfortable with. You deploy securely to the container services, and voila, everybody can use it. Everybody has a secure latest image that your organization can use. This is the tools section of it. So all the 5 stages are here, and this is from Microsoft documentation itself. So you could use any of these tools from Docker Hub, GitHub repository, or any other container registry, for example. There are minimum quality bars, minimum quality stars that you could use, although they cannot always be trusted. You go ahead and acquire the image from there. You generate the software bill of materials, which is basically telling you what all is installed there. So now you have proper documentation to check if these things are secure. You scan for vulnerabilities and you scan for malwares, and then only you go to the next stage, which is the cataloging. Now you have information about the image, you have the image, and then you go ahead and continuously scan it, generate metadata around it, and make sure that it's taken from approved resources. Now we have this cataloging stage done, we have the image under control, we have listed the kind of vulnerabilities it is. It's now time to remediate that. This is where all those vulnerabilities that we are remediating goes into build stage. So we now have a life cycle to make sure that whenever we update, those vulnerabilities are remediated. We have metadata we build for scan and fix the vulnerabilities, sign the image, very important because this is the identity problem. If the image is signed, then you know where it is from, but apart from your organization, nobody can use it. That makes it so much easier to trust the images that you're using. We sign the image and then we deploy it to our compliant environment. Keep the artifact updated, deploy policies, and keep checking if things are happening in the runtime for monitoring purposes. And then we see if there's an abnormal activity or if we have to clean something or a malware or vulnerability is introduced, we attack that. All of these stages have mentioned different kinds of tools. For example, the first one is container registry. And the Defender is always there because tools like Microsoft Defender, there are other cloud resources too, which continuously monitor such resources for you. Trivy and Copa are used for generating cataloging information and checking out vulnerabilities, and they're used in multiple stages. And then there is DevOps for pipelines, and Dependabot and Copa to checking out if there are vulnerabilities and how those vulnerabilities can be remediated. Helm and everything else is for infrastructure compliance. So we harden, we make sure that only certain images are used here. And then we sign it with Ratify and Gatekeeper, make sure that only signed images are used. So even if a rogue developer wants to do something, they're not able to do it because it's not allowed by the organization through policies. The policies are implemented by policies and they're probably checked by Gatekeeper. We want to explore a couple of tools here till Ratify. I'm not going to go through Gatekeeper. It's kind of a complicated setup. But if you're familiar with containers, you're probably familiar with Kubernetes. It's used to run multiple containers and synchronize them and operate them. So this is what we're going to do. We're going to build and push to pipelines, scan for vulnerabilities, create a software bill of materials, attach those artifacts to container images, sign those images, and push it back to ACR and pull again. All of this demonstration is a screenshot here because, God forbid, demo gods might interfere. So we've taken a screenshot. I've taken a screenshot by screenshot of each stage. And all of this is available at GitHub in the repository. So we're going to go ahead and start with downloading and checking the image. So if you notice, a couple of pipelines are available here, and this pipeline would be available in GitHub too. These are different stages. So what I've done is I'm trying to go ahead and download the image for one of those programs. Just this could be any program, by the way. This could be any container image. So the name doesn't really matter. The point here is that we've downloaded Trivy in the same pipeline, and I'm now trying to go ahead and generate what is the kind of software and what kind of runtimes and binaries are installed there. And it's not very difficult. Trivy is an open source tool. A simple command line with Trivy just goes ahead and executes it. And this is the command line here. If you notice here, I'm running a pipeline, and the command that it's executing is trying to highlight the image, and it's trying to highlight if the image has certain severities or vulnerabilities that are marked as high and critical. The reason Trivy can do it, Trivy mostly has these things cataloged. It works with a catalog. And this is what it has found. So now we have a couple of CV vulnerabilities which are high and critical in nature, and the status is around the installed version. So it might be an old version that has been installed there, and that's what's leading to that. Again, after I do that, I go ahead and create a JSON file that goes ahead, gives me the list of softwares that are installed there because I need those. And the reason why that is needed is for the audit purposes and for trackability. It's a good practice that when I use a software like this, the software bill of materials is always kept in focus because that is your defense against the supply chain attack. Otherwise, it's almost impossible to track where the supply chain attack actually originated. And that's one of the reasons why I'm doing it. And the reason why we'll be keeping it with the registry and not in the GitHub is because whenever somebody pulls from the repository, they get all these artifacts also. If you push it in your repository itself, which you can do and which you probably should do as a duplicate, the other people who are going to use the image will not have the same information. So as an administrator, you should probably push it into the container registry. Now, when this is happening, the Azure Container Registry is OCI approved, so Open Container Initiative. So it can absorb not just container registries or registries in general, it can also absorb these artifacts, which are software bill of materials and the list of the software that are installed there. Yeah. Cool. And well, I'm running out of breath. And now we go ahead and scan all of these scans. I'm attaching the list here and outputting it as a software bill of material and pushing it to the container registry. Yeah, we first scanned that and now I'm scanning it into a file. And these are the list after I pushed it to container registry here. And this is where I pushed it to Azure Container Registry. And if you see here, they're uploaded and we could list it here again. So not just the image, there is a checksum, which also gives you the information about both the files that have been updated there. And this is very important to understand that they are not tampered by some internal malicious actor. They always have this verification going on with the timestamp and everything. This could always be logged. Yeah. This is the view in the container registry. So it's not just the image, there are other artifacts too. The same if you want to pull it out with ORIS command line, which is again Open Container Initiative, you could pull it out from there. It gives you the same information there that you are able to pull the container registry and software bill of materials and the information about the binaries too. The same happens to every developer who wants to work with this container registry. And if you notice here, this is the information about what is installed in the container image and what's being supplied to you in your image. So it's possible to keep a track of it. And this file could be used with Sonar Cloud and many other tools to check if the softwares that are installed in your image are vulnerable. And you can put that information in your pipeline also as a gate. Cool. Now we go ahead and now assuming we've verified and everything, let's go ahead and sign the container registry, which is very easy again. We can go ahead and sign with the help of Notion. Notion is a tool, it's open source, and it's used to generate signature and sign the image. After we sign the image, we're going to go ahead and publish the artifact again. So if you notice this here, we've downloaded and prepared Notion with a couple of command lines. And I'm now signing each one of those artifacts, which is the container image itself, the software bill of material, and the list of softwares that are installed there. This now makes the image yours. So the organization is now responsible for it, and people who are going to use the image can use this signature to verify that the image is actually from you. So there's less conundrum around it, and your security teams are more in control. I published the artifact again, so now the signature file is also up there in the container registry. Next, we verify the artifact. We check it out, and this is what developers would eventually do. So now we've already verified and signed the image. We've updated the vulnerabilities and all of it for transparency, audit purposes, and security purposes. If you notice here, we have Notion again to verify if the signature is valid. So right now I've downloaded the content from container registry, and Notion is used to verify if the downloaded property has signature that is verified from the container instance. So if the signature of the image matches the signature that has been identified from container registry, then it has not been tampered with. Where did I go? Yeah. And after all of this is done, you could use in the next steps to go ahead and use this image and update it with the software that you want. Now, this was the view of the execution, but the code essentially is also not very difficult. So if you notice, I'm downloading through pipeline. I'm not keeping these resources in a virtual machine installed beforehand, and it's not a very difficult command line here. On this command line, I'm not sure if you could see my cursor, but yeah. So if you see wget, this is from Trivi's website. It's possible that the version might have changed, so you can use the same version there. After that, the Trivi same command line is used to go ahead and check vulnerabilities, and all of these command lines are available at Trivi's website. So you could just be copy and paste from there. ORAS is not exactly what is essentially. It's just to show that the container registry does work with Open Container Initiative, which is very handy to keep these things in a centralized location. So not just container image, but also SBOM and everything else around it. Yeah. So now all of these are small steps that are available as Azure command line or Bash. So not really steps available in DevOps, but you could just run the command line and that would just serve the purpose. The same is the case when I go ahead and verify if the artifacts are there. Yeah. So I used AZ login to log into the container registry and ORAS command to upload the artifacts there. Yeah. Then the list of artifacts is available, and I go ahead and query that again with the ORAS command because container registry is ORAS certified. And this gives me a trees view that we saw earlier. So that basically brings me to the end of the demo. And the summary is basically work in stages. Different stages have different tools and processes. Authenticity is very important. Do not use random images or container artifacts to start with. Always verify, work with your security team, get a verified source, maintain a verified source. And end-to-end observability is really important, as we did with the signature, and we could actually enhance it with logs and stuff. There are a couple of links that you could check it out, and it's mostly part of Zero Trust architecture. And because this is sort of a understanding situations, I've created a quiz. If any of you want to drop the answer on chat, A, B, C, D, just otherwise we could talk about this a little bit more. Why is container image signing important in DevSecOps? To reduce the image storage size, to automatically scale the container in production, to verify the image has been transferred, or to make image download faster? The answer is, again, to verify that the image hasn't been transferred. Another question, and this promise this is the last one. What is the primary purpose of generating SBOM, or software bill of material, in DevSecOps? Automate the container scaling in Kubernetes, list all software components or dependencies, encrypt the image, or monitor traffic in real time. Any takers? Well, it's to list the software and components. And that brings me to the end of it. And I thank you all for joining. See you on the next one. You have a lovely day ahead of you. Bye.